Let us see how to write a program for an NMOS 3-input NOR gate. Here, this simple circuit shows the 3-input NOR gate. The inputs are in1, in2, and in3. When we are going to see the particular logic here, the 3 transistors in1, in2, and in3 are connected in parallel. And the upper half section is a transistor Q4, which we can use as a pull-up section. Within the parenthesis, we can represent the net B. So pull-up B can be simply used for the transistor Q4. So coming to the logic here, so B is the output, nothing but it is the complement of in1, in2, and in3, which are odd together. In between in1, in2, and in3, the OR operation is being performed, and then the whole thing is being complemented, becomes the NOR operation. So when we are going to see the transistors here, all the transistors are of NMOS transistors. So that's why this circuit is nothing but NMOS, and number of inputs that are used for performing the NOR operation is 3 inputs. So it is 3-input NOR gate. So how to draw this particular circuitry means we already know that B is nothing but the 3-input NOR logic whose inputs are in1, in2, and in3. Let us see how to draw the diagram for this at switch level. So below the complement, always the output is complement either in the form of either we are going to see the NMOS logic or implementing using NMOS logic or CMOS implementation. The output is always in complement form. So B is nothing but in1 odd with in2, odd with in3, whole complement. So we have to see the logic below the complement. Here the logic below the complement is in1, odd with in2, odd with in3. So let us see an example using switches and lamp. Here the switches called as A and B, they are connected in series, and we are going to connect some battery B and the lamp L. So when the switches A and B both are ones, then only the lamp will glow. If both are zeros, lamp does not glow. If any one is 1, 0, 1 combination, lamp does not glow. 1, 0 combination means switch A is on, B is off. In that situation also the lamp does not glow. And when both are ones, then only the lamp will glow. So if you are going to observe this particular logic, this logic is for AND gate. 2-input AND gate. So to perform an AND operation, we have to connect the switches in series. That is the basic thing that we have to remember to draw the circuit using NMOS or PMOS. So NMOS or CMOS. So similarly, let us connect the switches A and B in parallel, and let us connect a lamp to which we are going to give some supply, a battery, fixed DC supply, and when we are going to see this particular arrangement of switches, inputs are A and B and the output is L. If both are zeros, then no current will flow through the lamp. Both are zeros means both are open circuited. So there is no closed thing. no current will flow through the lamp and the output is 0. If A equals to 0 and B equals to 1 means A is open circuited and B is short circuited. In this situation, the current flows through the battery through the B switch and then it goes to the lamp. So lamp glows in this situation. Again, when we are going to take one more combination, 1, 0. So A equals to 1 and B equals to 0. A is short circuited and B is open circuited. In this situation, the current will flow through the path of A to the lamp. So the output is logic 1. When both the switches are short circuited or logic 1, then again the lamp will close. So if you are going to see this logic, nothing but it's an OR logic. So to obtain an AND logic, the two switches must be connected in series, and to obtain the OR logic, the two switches must be connected in parallel. Now, how to implement this particular NOR means below the complement, whatever may be the logic, we have to observe that particular logic and accordingly we have to do the connection. So below the complement, in 1, in 2, in 3. These are the three inputs that are given to the three gates of the transistors. And these three transistors must be connected in parallel. Why? Because these are ORed together. We have to perform the OR operation between A, B here, or in 1, in 2 and in 3. Three inputs means in 1, in 2 and in 3. We have to perform the OR operation. So these three transistors must be connected in parallel. Coming to the upper transistor is the depletion MOSFET, depletion NMOS transistor. And the depletion MOSFET, when we are going to see the structure of MOSFET, and NMOS consists of p-type substrate, lightly doped p-type substrate, into which we are going to have heavily doped n-type source and drain. N-type source and drain. So, the path between source and drain, we can call it as channel. So, there is no physical connectivity or channel in an enhancement MOSFET. But in depletion MOSFET, there is a physical connectivity between source and drain, the two of n-type. So thereby, even we are not giving any voltage to the gate with respect to source, that is VGS equals to 0. In that situation also, because of the presence of a physical connectivity between source and drain, the MOSFET goes into on state whenever we are going to give some VDS. So this is the concept of the depletion MOSFET. So in this particular depletion MOSFET, this is the gate terminal and this is the source terminal. Gate and source are shorted together. Nothing but VGS equals to 0. Still, because of VCC, because of VDS, here VDS, nothing but VCC. Because when you are applying the VCC, automatically this transistor goes into on state. Now, depending upon the inputs that we are going to give here combination, accordingly, we are going to get the output B. This was the logic behind how to draw the particular representation. See, using CMOS logic or NMOS logic. We have to see the logic below the complement and we have to implement that particular thing with the help of transistors.